In this video, we're going to take a look at the electrophilic addition mechanism, and we'll look at a few examples to see how it works with our various different types of electrophilic addition reactions. So starting out with our general electrophilic addition mechanism, our first step involves the pi electrons of our double bond attacking the electrophile. So essentially, these pi electrons are acting like a nucleophile, and they are attacking our electrophile. So we show that with a curly arrow starting from our double bond and attacking our electrophile, which has a positive charge or a partial positive charge. And we'll see some examples of that as we go through some specific examples. That will create a carbocation. And the carbocation that's created is going to have the positive charge on the more substituted carbon. So this is going to be dependent when we see that we have some asymmetrical alkenes. We want to put the positive charge on the more substituted carbon. Our second step then involves a nucleophile attacking the carbocation. So we have a lone pair of electrons on our nucleophile, and we're showing a curly arrow attacking our positively charged carbon of our carbocation. And so this is going to create our alkane with our electrophile and our nucleophile attached on adjacent carbons. So let's take a look at some specific examples to see how this works. Now let's start out with an electrophilic addition of hydrogen halides. So the example I want to show you here is we're going to use but-1-ene. So I'm going to have our but-1. So we got 1, 2, and then we're going to have our CH2, CH3 here. Okay, and then we'll have a hydrogen there. And so let's do that reaction with HI. Now, if we recall here, we have a dipole where the positive end is the hydrogen end and the partially negative end is our iodine end. And so what's going to happen in this first step is we're going to get attack of our pi electrons to the partially positive end of our HI molecule. When that happens, the electrons between the bonds are going to break and go onto the iodine. So what are we forming here? Well, we're going to form a carbocation. And the important thing to remember here is that the carbocation we're going to form involves the more highly substituted carbocation. So we're going to put the positive charge on the second carbon here. And we're going to add that hydrogen to the first carbon. Okay, we'll get into why we do this in a second, but this is what happens here. Okay, the other product we've created is, and maybe I should do this in blue, is an I-. And so essentially we've generated a nucleophile in this step. So now our second step of our reaction mechanism is the lone pair of electrons from our nucleophile are going to attack the carbocation, the positive charged carbon, and create a bond there. So in our second step, we're going to create our final product here. So let's just CH2, CH3. I'll just put those together to make that a little bit easier. I'm just going to put the H over here so we can see that our H is going to add here and our I is going to add here. Okay, so we've created now a hydrogen added to one carbon and iodine added to the other one for our final product in this particular reaction mechanism. So the important things to show here are your curly arrows going from your double bond to your partially positive end here. It's important to show your curly arrow breaking the bond between the H and the I onto the I, and then showing your final curly arrow attacking the positive charge center in our carbocation. So I've kind of alluded to this a couple times in this video, but how do you know which carbocation is formed? Well, the one that's formed is when the pi bond is broken, it has a positive charge on the most substituted carbon. And that's because tertiary carbocations have the most stability. Okay, so down here, our tertiary carbocation is way more stable than even a secondary carbocation followed by a primary carbocation. And our least stable is a methyl group with a carbocation. Okay, so we always want to go with the most substituted carbon has the positive charge on it. So let's look at our next example here, and you're going to see this follows the same rhythm each and every time. So this time let's react ethene with bromine. Okay, so this is an electrophilic addition of halogens. Now, for the sake of this, I know that a bromine-bromine bond there's no polarity to it. But when we get electrophilic attack, we do create these temporary dipoles at each end of the bromine just by coming into close contact with the pi electrons of our double bonds. So we're going to attack one end of this bromine molecule. It's going to kick out and break that bond and create our nucleophile. So in our first step, we're going to create our carbocation. So I'm just going to draw it here. Our positive charge goes here. Now this is symmetrical, so it doesn't really matter, right, where we put our positive charge. But if it was asymmetrical, it would go on the carbon that's more highly substituted. And our bromine is attaching to that first carbon there. And then the other thing we're creating is our nucleophile, our Br minus. So then the lone pair of electrons on the Br minus are going to attack our carbocation center, and that's going to create our final product, which I'm just going to draw out here, a 1,2-dibromoethane. So let's put the bromines on both. So you can see, very similar pattern to the last example that I showed you. All right, let's look at our final example and do an electrophilic addition of water. So in this case, let's do propene. So we're going to create our double bond here. We'll have a methyl group on here and an H here. And then, like I said in a previous video, it's helpful to think of water as H and OH, because we're going to then have our dipoles here. We're going to get attack of that the pi electrons to the H side of the water molecule, and that will kick out and create an OH minus molecule. So let's draw the products of our first step here. Okay, so we're going to have our methyl group here. Let's draw the H's properly. We'll draw the H here. Now remember, the positive charge is going to go into the more substituted carbon, so it'll add to that second one there, and we'll create a hydrogen there. And then our other product is an OH minus with a lone pair of electrons. So we've generated our nucleophile, which will then attack the positive center of our carbocation to create our final product. So let's just draw in our final product here. We got an H, and then we have an H added here and an OH here. So those are our electrophilic addition mechanisms and some examples for halogens, for hydrogen halides, and for water. That's it for this video. We'll see you in the next one.